Alright, welcome to another video here, and now we're going to be looking at eddy currents. And eddy currents specifically within the syllabus are only mentioned down here when it talks about heat resistor production and eddy currents in terms of transformers. But we know that they ask them in other ways. Now, of course, one of the big things about physics is that you have to understand the underlying physics, and then of course no matter what they test you, you can transfer your knowledge to different contexts. And so they tend to ask you other questions like if we drop a magnet through a tube, what happens, right? And that's all to do with eddy currents. So let's explore what eddy currents are with some examples in this video, and then other videos when we talk about eddy currents it's going to add more to it. If you remember the mind map with Faraday's law and the relative motion of a conductor with a magnetic field, well, it's got eddy currents in there to do with electromagnetic braking and of course in transformers, but now let's look at them in terms of tubes as well. Alright, so what is an eddy current? Well, if you're doing any whitewater rafting, you may have heard of them before in terms of eddy currents with water. You can see with the video down here, I've got a river going around an obstacle, and look very carefully, the current comes around like that, and there's a little backwards current that forms on either side here. And this happens a lot in whitewater rafting where it's behind a rock, and that enables the rafter or the kayaker to have a moment's rest because they can hop in the eddy current. They're not moving down rapidly down the river. They can stay in the eddy current and then they can come out of the eddy current. So it gives them a moment rest. So a current that moves in the opposite direction in water is called a water eddy current. Well, what do you think happens with circular currents of electrons in metals? Eddy currents. So let's now have a look at an eddy current to do with electrons moving in a conductor. One area in which they test you this, of course, is dropping magnets through pipes. We've sort of seen this a little bit before. You know that when I drop the magnet, it's going to look like it's hovering inside the tube because it's got magnetic fields slowing it down. Let's explore this in terms of eddy currents now. We're adding the new terminology in our explanation. So if we drop it down a copper pipe, and you can see with the video there, that's what I did. I've got big copper pipes. I've got a big one that's quite wide, it's about there, and then I've got a smaller diameter one that's actually like a meter long. And when I drop those magnets through there, they slow down. And I usually do it during shows and so forth for younger kids. And I say to them, why does it slow down? And is it because they're magnetic? And of course, I show them that metals, such as copper and aluminium, are non-magnetic. How do they slow down? And then we talk a little bit about that. Now, a physics student, we of course know they slow down because there's relative motion between a magnet and of course a conductor. So as the magnet falls down, the walls of the conductor are exposed to a changing magnetic field. Now, because of Faraday's law, we get an induced EMF in the walls of the conductor. The induced EMF will cause a current to flow. Now, in this instance, the current is flowing in a circular direction, okay, and that of course induces a magnetic field, okay. And so the direction of that current flowing is according to Lenz's law. It'll flow in a direction to create a field to oppose the field that created it, right? Just falls off the tongue now. And if we have a look at our magnet, we've got north here and south here. So we want to generate a south pole here that's going to oppose the falling magnet and slow it down. And if you use our right hand grip rule, that tells us that on this side of the tube the current is going in and it's coming out on this side. So in other words, it's traveling in a clockwise direction if we view it from the top, right? So that's what's going on with the bottom one. If we look at the top, we want to create a south pole up there to attract the north pole of the magnet and slow it down. And so in order to do that, we use our right hand grip rule again, and our fingers go into the side here, we can see it there, and the current comes out towards you. And so from viewing from above, that's going to be an anti-clockwise direction. And so those eddy currents, these circular currents in the conductor, those eddy currents will cause the generation of a magnetic field that's going to slow the magnet down. And that happens in copper and aluminium and any metallic conductor that is non-conductive of magnets, right? If you put it in a stainless steel tube, the magnet's just going to attract to the steel. We don't want that to happen. We want a non-magnetic pipe. Okay, so let's have a look at a HSC question here. You've got 1.8 minutes to read it and to do it. I'll see you after that. All right, get your motor started. Off you go. All right, let's see how you've got. Did you get B? Well done if you did. Let's just talk about it if you didn't, and just to reinforce the content, I'm saying to you, reinforcing it verbally, drawing it, explaining it is good to do when you do questions like this. So a magnet passes through a conductor, a copper pipe, at constant velocity. Okay, the current is induced in the tube by the motion of the magnet. So we've got relative motion between a magnetic field and a conductor. Which row of the table correctly describes the force at P and Q? So if we're moving a magnet in this way, this end of the tube initially has no magnetic flux. Then as the magnet gets closer, we experience a change in flux, Faraday's law, which will induce an EMF in the conductor that will cause a current to flow in a certain direction. That current is called an eddy current. The direction of that eddy current will be, according to Lenz's law, in a direction that will create a field to oppose the change that created it, right? And so in order to do that, we want to produce a south pole here. Using our right-hand grip rule, we can tell that the current's going to go around this way. It's going to produce a south pole, and that's going to be repulsion, right? We go up this end here, we know that the moving away of a north pole means that there's going to be a change in flux. It's going to get lower. We want to create a pole that's going to increase the flux coming in. That's going to be a south pole. It's going to cause the flux lines to go in this way. So that south pole, if we use our right-hand grip rule, that tells us the current now goes in the opposite direction, right, around the outside into the page. And that's going to create an attraction, and that's our answer. Okay? All right, here's another one. You've got 1.8 minutes. Ready, set, go. All right, how did you go with this one? It's C is the answer. Let's have a look at this one. This may have tricked you, right? We know that a plastic is a non-conductor, so we know that's going to fall fast, okay? Over here, we got copper, and over here, we got copper. So what's the difference? Well, this is a complete ring of copper, whereas this one has a cut in it. What's going to happen with the cut? Well, the cut is going to stop eddy currents from forming, right? The current is not going to go around the ring because you're stopping it. You are placing an air gap there. So that means no eddy currents form, therefore no opposing field to slow the magnet down. So this one and this one will fall at the same rate. And then, of course, the middle one will be slower because eddy currents will form in the ring. That will cause a magnetic field to be induced around the ring to slow it down. And so these two will happen simultaneously. Q will be after, which is C. Okay, so that's that one. All right, what about this one here? Right, you've got 1.8 minutes to have a go. Off you go. All right, let's see how you went with this one. Did you get C? If you did, great. Could you explain it now to someone else? Right, that's what you want to do. Practice explaining it. And here we go. We've got two tubes, one plastic, one copper. They've got the same length and the same diameter. So we're keeping some variables the same. We've got the same magnet, okay? And we're dropping those magnets through that. What happens? It says, it's repeated. Which of the following statements is true? Well, C, the magnet will take longer to fall through the copper pipe. Why? Well, as the magnet falls through the copper pipe, of course, eddy currents are generated in the walls of the pipe because they are exposed to a changing flux. Those eddy currents will be in a direction to create a field that will oppose the magnet's field. And so we have a south pole here and a south pole there. That's going to slow the magnet down and therefore take longer to fall. The plastic, being a non-conductor, will have no eddy currents induced in it, and therefore magnet will free fall due to gravity through the pipe. So that's that one there. Okay, lucky last. Right, now this one here's a 4-mark question, so you get 7 marks for this one. Okay, so highlight the key words and have a crack at it, and we'll go through it in a minute. All right, let's see how you've gone here. Now you're going to have to mark it and see what you've got here. It's 4 marks. Which magnet leaves the tube first and why? Right, why? So if it's 4 marks, you're probably going to get 1 mark for getting the magnet correct. So magnet B leaves the tube first, right? Which magnet leaves the tube first? Magnet B, 1 mark, right? Why? This is worth 3 marks. So here is where you have to explain it. Now, if you explain it with just 1 magnet, you'll probably get 2 marks. To get the full 3 marks, you need to relate it to both magnets. Okay, so let's start off with magnet A. As magnet A enters the tube will experience a change in flux. That change in flux causes an EMF to be induced, which therefore creates a current to occur in the walls of the tube. The direction of the current is such that it creates a field that creates a magnetic field to oppose the one that created it. That's Lenz's law. This will slow the magnet down. So it's nothing new that we have seen before. Just make sure you're showing those links. As this happens, that causes that, which causes that, etc. And then link it back to how fast it moves through the tube. The second one is the one which of course goes faster. As it enters the slotted tube, the field change, or the change in flux still occurs. However, due to the slots, there are smaller surface area. That smaller surface area causes a smaller induced current. That smaller induced current, the eddy currents are smaller. Therefore, we have a smaller retarding force on the magnet, and overall, hence the magnet falls faster and exits first. So we're saying this happens, this happens, this happens because of this, and therefore it falls faster compared to the other magnet. So we're comparing the two, and that should give you the 3 marks there. So it's important you practice this, you articulate it, you're using evidence, and you link it back to the question. So that is it for this video on eddy currents. Hopefully you got a better understanding now. And now when we do other things to do with eddy currents, you've got this knowledge behind you to add into your answers. Because eddy currents are also tested in a variety of other ways, such as magnetic dampening, which is what we're happening next. In fact, dropping a magnet through our tubes is magnetic dampening. But we're going to look at an everyday example of magnetic dampening. And then there's other examples as well, like induction cooktops, etc., are all to do with changing magnetic fields, circular eddy currents being created in a conductor. So it's about using that physics knowledge to apply to another situation, which is where they test you in the exams. So as always, I hope that made sense for you. These videos, remember, for Module 6 are going on YouTube to show what we do in the school homework lab. If you like it, click like and subscribe, of course, and then come over to join us in the course, where you'll get access to all the posters for free if your school subscribes, and study cards, and worksheets and Kahoots as well, so make sure you do those. And if your school doesn't subscribe, then of course you can go to thecrazyscientist.com and you can buy them there as well. So until then, practice articulating it, do many questions, including what's below, and I'll see you in the next video.